All right, what up, everybody? Today we're talking about circular motion, and we're talking about specifically uniform circular motion, which is when an object moves at constant speed in a perfectly circular path. So obviously, not all the circular motion out there is uniform circular motion, because not all things move uh, in a perfectly circular path. Sometimes the path is a little bit oval, and sometimes things are kind of speeding up, slowing down a little bit. But by looking at uniform circular motion, we can get a good estimate on what things are doing that orbit, whether it's planets orbiting the sun, the moon orbiting the Earth, or just a rock tied to a string that's being swung around your head. Even cars turning on the road are part of a circular motion for a period of time. And so it's an important topic in physics, and we're going to look at how to find the velocity, how to find acceleration and force, and how those things work. So, first of all, let's look at how to find the velocity or the speed of something in uniform circular motion. Here's an example. Circaka roach is attached to a 1 meter string and swung in a circle. It takes 2 seconds for him to make a full circle. How fast does he travel? All right, so someone picked him up, tied him to a rope, and swung him in a circle. And the rope was 1 meter long, so his orbit was a circle with a radius of 1 meter. Let's think about, well, let's see what will happen. Okay, he'll go 1 meter, 2 meters, 3 meters, 4 meters, and when he goes 4 meters, he passes pi, 1.34 meters, and then 4 meters, 5 meters, 6 meters, and by the time he gets back to where he started, one full circle, he's gone 2 pi meters, right? So that'd be 2 times pi, or about 6.28, and then you can add on some decimals, right? Depends how nerdy you are. And so that's how far he's gone if he swings through a whole circle. Now, when you talk about speed, the way you always measure speed is just how far something's gone divided by how long it took. And so we'll do the same thing for him, right? His how far he went was 2 pi times 1, which was the radius, because if you go back, the radius of the circle is 1 meter. So the circumference, if you remember from geometry, is 2 pi times the radius, or just 2 pi times 1 meter. And then the time that he took to do that was 2 seconds. So we want to make an equation that can be used for any circle, right? Not just this 1 meter circle. And so to do that, we're going to replace the 1 meter with an r for radius. And we're going to replace the 2 seconds with a capital T, right? That gives us that equation right there. And the capital T is the period. And the period is the time it takes to make one complete circle. And so it's not just any time, it's a time for one circle. So if you have a problem where the thing doesn't make a full rotation, you would have to extend the time out to see how long it would take to go a whole rotation. Or let's say you have a problem where it takes 4 seconds to go around twice, well, you'd have to divide the 4 by 2 to get how long it would take to go around once. And that's how long it takes to go around once is the number you put in for the capital T. Okay, so that gives us how strong the velocity is, or in other words, what the speed is. Now remember that velocity is not just how fast, it's also what direction. Right, so this just tells us the magnitude of the velocity, not the whole velocity. Let's just get the whole velocity. You need the direction. Okay, and the direction of the velocity in a circular motion is always perpendicular to the radius of the circle. Okay, so you imagine you draw a line from where the object is to the very center of the circle. 90 degrees to that line is the direction of the velocity. Okay, so obviously that's always going to change because the thing keeps on moving, so the line perpendicular to the radius keeps on moving. And we'll see that in a little bit. Acceleration. Okay, so you might ask, well, how can you possibly have acceleration if the velocity is not increasing or decreasing, right? And the reason you have acceleration is not because it's speeding up or slowing down, but because it's changing direction. And changing direction means it's changing velocity. even though the number itself is not changing. So that's a little bit different than what we're used to in straight line motion. But nevertheless, there is an acceleration, and it can be quite strong in circular motion, even if the thing's not speeding up or slowing down. And in uniform circular motion, the acceleration is equal to the velocity squared divided by the radius of the circle. Okay, so that would be your equation for acceleration. If you remember Newton's second law, you can find the net force on an object by taking its acceleration and multiplying it by its mass. So we're going to do that. And there you have, that's how much force an object experiences when it's in uniform circular motion. And it's always going to experience that force, or else if it didn't experience that force, it would no longer be in uniform circular motion. It would go off the circle. So mass times velocity squared divided by r. That force is always directed towards the center. So here we have an object here at the intersection of the two lines, and that object is moving in the direction of the blue arrow, and it's being forced to the direction of the red arrow, right? And you can see that as it moves around the circle, the velocity is always 90 degrees angled to the force, and the force is always directed towards the center of the circle. Okay, and wherever the force is directed, the acceleration is also directed. So you have something moving this way, but accelerating this way, and as a result, you get a circular path. Okay, so again, this is how it works. The direction the object moving is shown here, and if there is no force, then the object's momentum would keep it moving in the direction of that blue arrow. But there is a force towards the center of the circle, and if there is no velocity, just this force, then the object would just fall towards the center of the circle. But because there's a velocity and a force, then the resulting motion is a compromise between the two, and that's how you get this green curved dashed line right here, which shows which direction the object is actually going to go. Right? So you can imagine there's a object, and you have a object in circular motion, for instance, a planet going around the sun. If the velocity is just right, then the force and velocity are going to both affect the motion so that it goes in a circular path. Right? If the velocity is too slow, right, then what's going to happen is it's going to get closer and closer and closer to the sun. Okay, and eventually it's going to spiral into the sun until it's burned up. But if the velocity is too fast, then it's not going to be a circular orbit. It's going to be more of a oval. Okay, and if you know anything about the solar system, this is true of the Earth. The Earth has a orbit that's slightly elliptical, slightly oval, and so that means that the Earth's velocity is just a little bit more than it needs to be to stay in circular motion. Okay, which is good for us because we don't want to spiral into the sun. All right, so that's an intro to circular motion. I will see you all in the next video.